Okay, continuing with 8.2, finding the area between two curves. We left off on our last video with this example, our last example of this lesson. We have the cubic function y equals x to the third. We actually graphed out the sideways parabola x equals y squared minus 2. We also talked about how we could solve that sideways parabola and come up with this alternate way of looking at it. You'd have a radical x plus 2 or the opposite of radical x plus 2. Suffice it to say, you've got this enclosed region, and the real question is, could we find the area with respect to x or with respect to y? The answer is actually either way you honestly could. One way is considerably easier, though. What I do want to point out, though, is that very often when we're finding these problems, you'd probably like to find points of intersection. Uh, the lower point of intersection, again, you might just try with these two curves to see if there's a friendly point. In that third quadrant, it looks perhaps like maybe we could have the point -1 plugged in for x. On the cubic function, you'd have the point -1, comma -1. If you check on this sideways parabola, if you let y equal -1, your x would be -1. So you could, this is called solving by inspection, and you could very quickly, a lot of times, just find that a friendly point just does in fact happen to work. That being said, no matter what you try in that top right corner in the first quadrant, 1 comma 1 is not going to work. So we're going to need to use our calculator to help us to find the point of intersection. I've already jumped ahead and entered in y equals x cubed for y1. For y2, we're going to type in the square root of x plus 2, solving for y. And if you were to very quickly graph zoom decimal, you would see that you have your cubic function, and then you have your y equals the square root of x plus 2. Again, a very powerful tool is the intersect tool. Second trace, actually going to second calculate. We'll go to the intersect, choice 5. We'll say first curve. Well, clearly it is the cubic function. You can even see in the top left corner of the calculator screen it says that. Second curve will make the radical x plus 2. We'll say guess. Put your cursor right there. Sure enough, we get a point that's actually not very friendly. 1.214 and also about 1.793 for y. You know, what we can do is store this. I'm going to go second quit. And when I hit X, you can see you've got your 1.2148. I'm going to store this in. I'm going to say maybe make that alpha C. And that way the calculator will always remember not just the first couple digits after the decimal, but really as many as can be stored. You might wonder if we could get Y, the Y coordinate. If you hit alpha and then press 1, Y shows up. You'll be pleased to see that this was the Y coordinate that we just found. I can store that as alpha D and hit enter, and then you're good to go. Now we're going to use this in a little bit, but for the moment I'll say here's 1.214, and we called that C. You can see that our Y was 1.793, and we'll call that D. And the reason why you'd like to keep those stored is you'll need your fnint tool to be able to work this out. You might wonder if perhaps since we just talked about working out this problem with respect to y, if we could do that. A quick comment is you're looking at the problem with respect to y. I do want to point out that clearly anywhere in this yellow region, if you were to draw a horizontal rectangle, or even a horizontal segment for that matter, you would see that you'd always have the same right-left boundaries. You would always have the cubic curve off to the right, and off to the left you would have this sideways parabola. The sideways parabola, of course, would be given to you as x equals y squared minus 2. So with respect to y, what I'd like to do very quickly is integrate, and we need to go with our smallest y value. Our smallest y value at the very bottom of this region is -1. Up on top, if we were to go all the way up to the very top of this curve, you'd see that the y value that we have is 1.793, but I've stored this as alpha d. Now, when we're integrating with respect to y, we're always going to have right minus left. Again, this is our newer type of integration. And of course, what we need to do is always get x equals for our functions. We need x equals some function of y. Now, we said we had the cubic function. It's very tempting to put x cubed in, but what you really want to do is plug in the cube root of y. X equals the cube root of y here. We need x equals some kind of function of y. That's your right boundary. On the left, as you're looking at this sideways parabola, thank goodness this was already in the form x equals. And very nicely, we could come up with something that looks like so. Now, it would only take a moment to actually get this worked out on the calculator. If we typed in this integral, and if we were going from -1 up here, we'd just have to type alpha d. And then from here, you could see that we're typing in the cube root of y. Now, look, I know sometimes kids get a little worried about this. I'm going to actually type in the cube root of x here. You could actually put in a y, don't get me wrong. I think it's just easier to type in x when we're using this tool. But if you want to type in a y, it would be fine. It's just that we do this far more frequently, typing in x for both. And then, of course, we'll use parentheses all around that. Hit enter, and you can see it looks like we're going to be getting an answer. It's still thinking through this. It's taking a little while, about 4.214 or 4.215. So, nice thing is we don't need two integrals to do that. And again, feel free to retype that in all with typing in y's in place of x. You'd have to type in a dy also, but either way is good. Now at this point, you're probably thinking, well, wouldn't integrating with respect to x give us exactly the same thing? I'm sad to say it won't. Look, if I may just for a moment point out that when we're integrating with respect to x, we're going to always have not a right minus left boundary, but a top minus bottom. And at first glance, you look over here and you can see, oh, my top boundary would be that sideways parabola. My cubic function would be down below. But it's off to the far left region where all of a sudden we're going to realize things aren't looking very good right here. You can see this red rectangle that I just drew, the top minus bottom boundary, actually breaks the mold, so to speak. Our bottom boundary for that rectangle right there is not the cubic function. It's actually the other half of that sideways parabola. So again, just to point out something again, the top half of this parabola was y equals positive radical x plus 2. The bottom half of it was the negative radical x plus 2. So if you want to see, this whole thing getting typed out, you might notice when we had this on the calculator, we didn't see exactly what we graphed by hand because I didn't type in the negative radical x plus 2. Once you do that, now it's going to look just like what we had earlier. So again, what I'm trying to point out is that sadly, as we're looking here, this region right over here has a change in boundaries. You can see it's at x equals -1, where we're in some trouble. We'd have to set up two integrals to be able to deal with this. And let me show you very quickly what that would look like. To the left of this red line, we'd be integrating from -2 all the way up to -1. X equals -1. Top minus bottom. Well, you'd have radical x plus 2. That's your top. What about your bottom? We're going to have the negative radical x plus 2. So you can see here it's highlighted in blue and green. Make that rectangle. You've got the top radical for the upper boundary, the negative root x plus 2 for the bottom. Then I'd have to say plus. Well, if I went from -1 all the way out to c now, because c right here, 1.214, that's the end of my x values as I'm building from left to right. If I did the top, now you could see that I would still have radical x plus 2, but the bottom would just be x to the third. Again, what's the world of difference here? You can clearly see that now all of my functions have to be y equals functions of x, not x equals a function of y. But the boundaries have changed. If you work this all out, you'd get the exact same answer that we did when we integrated with respect to y. But this is more work. Obviously, we would prefer to deal with the simpler situation. Well, hope this is helping. Best of luck to you.